Now let's discuss the idea of left orthogonality. Sorry, left eigenvectors. So Ax is equal to lambda x is what we've seen as eigenvectors, right? So there we are actually right multiplying by a vector x. So in a similar fashion, we can also left multiply by a row vector, and it can also, so such an eigenvector is known as the left eigenvector. Okay, let's look at the definition. For example, if y is not equal to 0, similar to the condition which we had for eigenvalues, and c is equal to n. Sorry, it belongs to Cn. Note that eigenvalues only exist for square matrices. Is a left eigenvalue of A Cn cross n if y Hermitian A is equal to lambda into y Hermitian. So if you left multiply by the transpose of this, or the Hermitian of this uh, vector, which in turn will become a row vector, you will get lambda times y Hermitian for the corresponding lambda which is belonging to the uh, spectra of it. So it turns out that the spectra of A is actually the same as far as I know. Okay. Now let's look at the theorem, which is known as the principle of biorthogonality. So what this says is we have a matrix A, which is a square matrix Cn cross n, and we have two eigenvalues, lambda and mu, which belongs to the spectra of A, such that lambda not equal to mu. Then any left eigenvector of A corresponding to mu is orthogonal to the right eigenvector of A corresponding to lambda. So you take any left eigenvector. So this is not the case with lambda equal to. So if it's the same lambda, this will not hold. If it's valid for any other lambda, we have two sets of uh, eigenvalues, and we have two corresponding eigenvectors corresponding to it. And if y Hermitian is the y is the left eigenvector and x is the right eigenvector, corresponding to eigenvalues lambda and mu, then they have to be orthogonal. This is known as the biorthogonality. This is actually simple to prove. So let y belonging to Cn be the left eigenvector corresponding to the eigenvalue mu, and x be the eigenvector corresponding to the eigenvalue lambda. Okay, so if you take this quadratic form, it's not exactly quadratic form, it is scalar. You can see that scalar. Why it's a scalar? Because A is n cross n, this is 1 cross n, this is again n cross 1, this will be 1 cross 1. Anyways, so y Hermitian Ax. So if you pair A and x together, A and x is lambda x, which is indeed lambda into y Hermitian x, right? Similarly, y Hermitian Ax also, if you pair together y Hermitian and A, is equal to mu into y Hermitian x, right? So since both left sides are equal, you can equate the right sides as well. So which implies that lambda into y Hermitian x is equal to mu into y Hermitian x. So since lambda is not equal to if two numbers have to be equal and lambda and mu are not equal, the only way this is possible, as lambda is not equal to mu, is that y Hermitian x has to be equal to 0. So y Hermitian x is equal to 0 implies y is perpendicular to x. Hence, it's proved. Okay, so what does this say? This theorem again, let's repeat what this theorem says. If we have a left Hermitian, a left eigenvector corresponding to an eigenvalue mu, and we have right eigenvector x, which is corresponding to an eigenvalue lambda, and where mu is not equal to lambda, these eigenvalues are distinct, then these eigenvalue vectors are mutually orthogonal. Okay. So this is something like a result which can be easily proved. If x is an eigenvector of A, then x transpose is an eigenvector of A transpose. with the corresponding eigenvector lambda. Well, we've seen similar sort of results at multiple places where we're trying to find the eigenvector of P of A. We have polynomial, which is P of lambda. Similar to that, if you take the transpose, then its corresponding vector is X transpose, but the eigenvalue will be same. Why the eigenvalue is same? Because the eigenvalue is actually a scalar. The transpose of a scalar is the scalar itself. Now let's look at another theorem. This is also okay. The theorem here, what it says is, if A, B belong to C n cross n, we have two matrices, comatrices, and X is an eigenvector of B corresponding to a lambda. So lambda and X are an eigenvalue pair, and it is an eigenvector of B, of matrix B. And if B is similar to A, so we know an eigenvector corresponding to the matrix B with an eigenvalue lambda. Then we know that A and B are similar matrices. Then Sx is an eigenvector of A with corresponding lambda. So if two matrices are similar, we've seen that they have the same characteristic equation, right? The same characteristic polynomial, and it's the same set of eigenvalues. So we've already seen that, right? Okay, what about the eigenvector now? So Bx is equal to lambda x, right? Because x is an eigenvector of the matrix B. And we know S inverse A is equal to B. So if you substitute for B, S inverse A is equal to lambda x. Then if you multiply with S, left multiply with S on both sides, we'll get S into S inverse will become identity matrix. So A into Sx is equal to lambda into Sx, which means that lambda is an eigenvector, sorry, eigenvalue of A, while its a corresponding eigenvector is S into X. To make sure that X is not equal to 0 and S of X is also not equal to 0. Right. Because eigenvectors can't be equal to 0. Now let's look at another result, which this result is actually important. What this says is the eigenvalues of a real symmetric matrix or a complex Hermitian matrix are real. So what is a real symmetric matrix? A real symmetric matrix, it means A is equal to, let's say Q is a real symmetric matrix, Q is equal to Q transpose. Q may normally use for orthogonal matrices. Okay, we'll say A is equal to A transpose. Similarly, where A belongs to Rn cross n, this is a real symmetric matrix. And what is the Hermitian symmetric matrix? Hermitian symmetric A is equal to A Hermitian, and A belongs to Rn cross n. So in both these cases, whenever we have a symmetric matrix or a Hermitian matrix in general, so this is not Rn cross n, this is Cn cross n. We have a Hermitian matrix, then its eigenvalues are real. Okay. How do we prove this? So for a Hermitian matrix, we know A Hermitian is equal to A. And A into X is equal to lambda X. Why? Because lambda is an eigenvalue and X is an eigenvector. Fine. Now, we left multiply with X Hermitian, right? Now, if you multiply with the X Hermitian, this is actually like the quadratic form. X Hermitian Ax is equal to lambda times X Hermitian X. Okay. Now, if you take the Hermitian of this is a complex conjugate, right? This is a scalar, and its Hermitian is basically its conjugate. So X Hermitian Ax whole Hermitian is equal to X Hermitian A Hermitian X, which in fact is X Hermitian Ax. X Hermitian A into X. Okay. So which is in fact yes, lambda. Why is it lambda star? Oh, this is that's not required actually. Okay, okay. So this is actually lambda into x summation x, and this is actually the conjugate of that. So this is again. So this has been, the left side will be equal to lambda star x summation x. Fine. So which means that x summation x and x summation x can be cancelled out because it's a norm, and they are both not true. Anyways, not sure about this thing. So here, this is a quadratic form. The conjugate of this is same as that value. So this is something like we are saying this is a complex number, and let's say that complex number is given by, let's say, c. Z is equal to c conjugate. Z equal to z conjugate, it means the imaginary part is actually 0. So it means c is equal to lambda is real. So this is actually easy to prove. Just have to take the quadratic form and take the conjugate of the quadratic form, and the quadratic form happens to be lambda into x inverse x, and the conjugate of that is actually lambda star h x inverse x Hermitian x. Both are equal. So in fact, lambda is equal to lambda star, which means that lambda is real. Okay, so let's then end the discussion here.